quantum field theory. Quantum field theory is, of course, the description of nature as we know it, with the exception of gravity. So, practically everything that we know, with the exception of gravity, in principle, we think, is explainable if only we had the computational power to be able to solve quantum field theories with the accuracy that would be appropriate. Now, the problem is, of course, that problems tend to be much too complicated to solve, except for some very special problems. You can understand the hydrogen atom, but by the time you get to the boron atom, they're too complicated, and so forth. And certainly studying human beings is well beyond the capacity of any quantum field theorist that I know. But nevertheless, apart from gravity, quantum field theory seems to be all there is, and we're going to enter into the study of it today in a very, very, very elementary way. We're going to study today the idea of what is called second quantization. But before we do, and second quantization is about quantum fields, but we'll come to it, I want to review something first and maybe generalize that something a little bit. The thing that I want to study, or to remind you of, or go through with you, is again the harmonic oscillator, but a new aspect of the harmonic oscillator, a couple of new aspects of the harmonic oscillator, just so that we have it in front of us, because the harmonic oscillator is the central ingredient, the central mathematical structure that goes into quantum field theory. So we need to understand it, make sure we understand it well. But we're not going to worry about springs and systems oscillating. When I speak about the harmonic oscillator, I'm really speaking about the algebra of those little operators A plus and A minus, and the product of A plus times A minus, which is what, do you remember? What is it? It's the number operator. It's the number of the excitation. So I'll remind you now. We'll go through it a little bit, and I'll tell you one or two facts that I may not have told you about. What I'm particularly, all right, so let's just write down the rules for a single harmonic oscillator. A pluses, they act on states to elevate them up to the next level. There are A minuses, which take you down. At the bottom level, the ground state, A minus gives you nothing. It just annihilates the state. All right, so A minus is the lowering operator, and A plus is the raising operator. We're going to learn to call them creation operators and annihilation operators. What is it that they create and annihilate? As we'll see, particles. But let's just use the same conventions that we've used up till now. And there is also A plus times A minus. That was the thing, if you remember, that went into the Hamiltonian. You remember the Hamiltonian was just basically A plus A minus. What was it? A plus is x plus I omega p divided by some square root of 2 omega. A minus is the same sort of thing with a minus sign in there. And if you multiply them together, you get things with x squared plus, do I have that right? P plus, no, I have it wrong. It's P plus omega x. And if you multiply the two of them together, you get P squared plus omega squared x squared plus this extra little term that was the ground state energy. And so that went into the Hamiltonian, A plus times A minus, and we called it the number operator. It was the thing whose eigenvalues, whose observable values, were the integer level spacing, or the integer levels of the harmonic oscillator. So I believe we called this capital N, if I remember. And its eigenvalues we called little n, the observable values of it. One more thing, the commutation relations of A plus and A minus. That's what made, A plus and A minus are emission conjugates of each other. That's an important mathematical fact. But the other mathematical fact is that the commutator of A minus with A plus is equal to 1. That's what made everything work. That's what we used to find the properties of what happens when we act with A plus and A minus. We used those commutation relations. That was basically it. That's all that went into the harmonic oscillator. Now, I'm going to suppose I have many harmonic oscillators. You could just think of them as a collection of springs. Or you could think of them as the various oscillations of a violin string, or whatever, for whatever reason, there happen to be many independent systems that are undergoing oscillation, or that can undergo oscillation, possibly with different frequencies. Where does the frequency come into all of this? The frequency, well, first of all, it comes in here, but by the time we get to that point over there, the place where the frequency came in was just the fact that the energy is equal h bar times the frequency times this n here. There's also plus a half, or I'm going to leave out the half, the ground state. It's not important for us. Right, so that's where the frequency came in. It came in just as telling us what the energy for each increase of the number operator was. The frequency, together with h bar, determine each time we go up a level how much energy it costs to jump the oscillator up one level, or how much energy we might get back in some other form if the oscillator jumps down. It jumps up for some reason, that's how much energy we have to pay, h bar omega. If it jumps down, that's how much energy we get. And as I said, that's a single harmonic oscillator. But now if we have many harmonic oscillators, we can label them. We could label them with an index. And I'll use the index I, but I does not stand for the square root of -1. It's just a label which goes over all the possible oscillators that I'm interested in. There may be a finite number, there may be an infinite number. In the examples that we'll be interested in, there are an infinite number. All right, so now we get to label the oscillators. Just by putting in, well, okay, we have to be a little careful over here. Each oscillator, think of it as an independent system, as a system which is just an independent degree of freedom. And when you have independent degrees of freedom, the operators for one subsystem commute with the operators for the other for any other subsystem. That's a rule. We went through it 2 years ago or a year ago, whenever it was. The operators describing system A and the operators for describing system B, if A and B are truly independent systems, they commute with each other. Why? Because to not commute would tell you that you cannot measure them independently. If you can't measure them independently, they're not independent systems. So presumably if you had two springs, you could take one off way over there and the other one way off over there, and there's no reason why they should influence each other. They're operators, everything about them commutes. And so we can write the following, that let's write out all the commutation relations because they're important. Forget this for the moment. Let's first take the commutation relations of the lowering operators. I with J. The first oscillator with the 14th oscillator. Well, first of all, if I is not equal to J, they're talking about different oscillators. If we're talking about different oscillators, they must commute. But if we're talking about the same oscillator, then the commutator should be exactly the same as it was for the single oscillator case, namely 1. So how do we write that? We write that by putting the Kronecker delta over here. All that means, zero. Annihilation operators all commute with each other. Even for a single oscillator, the annihilation